Hi everyone, welcome back to chemistry. In this video, we're going to start chapter 10, which is all about acids and bases. On the right here, you can see the pH scale, which you may or may not be familiar with, and don't worry, we'll talk about it at length in this chapter. But we're definitely familiar with some acids and bases. So we're familiar with acids and bases in lab, right? We work with hydrochloric acid a lot. We work with NaOH or sodium hydroxide, which is a common base. But we're also familiar with acids and bases in our daily life. So if you've ever used lemon, that's pretty acidic, right? When you bite a lemon, it's pretty sour. It's got that characteristic sour taste that acids have. And then something like soap. Soap is actually one of a common base, a household base. Things like soap or cleaning products typically tend to be pretty basic. But what if we wanted kind of more of a textbook definition? Well, there was a Swedish chemist named Svante Arrhenius who developed kind of the first chemical definitions of acids and bases, and that was in the late 1800s. And what he said was that an acid is a compound that increases the concentration of the hydrogen ion in aqueous solution. So remember, when we say aqueous solution, we mean dissolved in water. So if you look at this this equation here, you'll see that we're taking some HCl or hydrochloric acid, and then we're dissolving it in water. That's what this H2O above the reaction arrow stands for. It means we're dissolving it in water, or reacting it with water. You could think of it like that as well. And what ends up happening is we end up splitting up or dissociating those ions in our HCl completely. So what ends up happening is we get chlorine turning into an ion, so the chloride ion, right, which will have a -1 charge because it's in group 7A. So it's going to want to gain 1 electron. And then hydrogen is in group 1A, so it's going to want to lose 1 electron usually, that's going to form the hydrogen ion. So when we put this HCl in water, it's going to dissociate or break up into these ions. And so because hydrochloric acid ends up increasing the concentration of H plus in solution, we can think of hydrochloric acid as an acid. Another way you could think of this in a little bit more of a kind of quick definition, and the way I like to think about it, is that an acid is something that donates a proton in solution. Donates a proton, H plus. Now, why do I say proton when I talk about H plus? Well, remember that hydrogen, it's number 1 on the periodic table, atomic number 1, which means it has 1 proton and 1 electron, right? Neutral hydrogen. So if hydrogen loses that 1 electron that it has, all that's left over is essentially a proton, right? So scientists will often use the term proton and H plus interchangeably when we're talking about these hydrogen ions or acids and bases. Arrhenius also had a definition for bases. He said that a base was a compound that increases the concentration of the hydroxide ion in aqueous solution. So remember, hydroxide is one of those polyatomic ions that you needed to memorize, OH minus. So he said that this any base is going to be able to increase the concentration of this hydroxide ion. And you can see this again. So this is sodium hydroxide, one of our common bases that we often use, and you've used it before in lab. And again, we're dissolving it in water, so getting into an aqueous solution. And what ends up happening once we do that is, again, we get this kind of dissociation of these 2 ions. And we have our sodium ion with a positive charge, and our hydroxide ion with that, characteristic OH minus, right? So again, you can kind of think of this as a base is anything that donates a hydroxide ion in solution. Donates a hydroxide ion. And what's nice about the Arrhenius definition, and we're going to talk about a different scientist's definition of acids and bases, because there's a couple ways you could think about it. But what's nice about Arrhenius's definition is that a lot of times you get a little bit of a hint, because usually our base is, if it's got hydroxide in it and it can donate an OH minus in solution, it'll say that in the name. So something like sodium hydroxide or potassium hydroxide, those are some common bases. And you get a little bit of a hint there that they can donate the hydroxide ion. So these are just some common acids and bases. I just wanted to show you guys some of these. You don't have to memorize all of them, but I'm going to highlight the ones that I do want you to memorize, which are, and this will just make your life easier. So the first one I want you to memorize is HCl, hydrochloric acid. I also want you to memorize hydrobromic acid, hydroiodic acid, and sulfuric acid. Oops. And nitric acid as well. So those are the ones that I want you to memorize for our class. As for bases, it's a little bit easier to memorize them because most of the ones that we're going to work with in our class are ones that end with hydroxide. So something like, NaOH, sodium hydroxide, that's a common base. KOH, potassium hydroxide. Magnesium hydroxide, calcium hydroxide, things like that. Those are some common bases. So why do we care about these acids and bases, in chemistry? Why do they matter? Well, it turns out that acids and bases will react with each other in chemical reactions, and when they do that, they form salts. Now, a lot of times we think of salt as, our generic table salt, right? NaCl. But there are actually a lot of different kinds of salts. So a salt is just kind of a general chemical term for any ionic compound that is formed from an acid and a base. And what happens when we react these acids with bases is we always get out two things, water and salt. It doesn't, again, have to be salt as, NaCl. In this example I'm going to show you in a minute, it does happen to be NaCl, but it's not always. It's just any ionic compound that's formed from these acids and bases reacting together. And this is called a neutralization reaction, or sometimes you'll hear acid-base neutralization reaction specifically. A neutralization reaction. And this is because when you react an acid and a base, they neutralize each other, right? And if you look on the left side of this equation, those are two things that we don't really want to touch as humans. NaOH is pretty caustic, right? It's a base. HCl is a strong acid, so that one can do quite a bit of damage as well. But when we react a base and an acid together, we neutralize those things. And what you get out are these substances that we eat, drink, touch all the time, right? Water and salt. So we neutralize those acids and bases. So this is one of the most common acid-base neutralization examples, this reaction down here. So we have NaOH, which is sodium hydroxide, reacting with hydrochloric acid, and it's producing NaCl, our salt, and water. But now how does this actually happen? Well, what's actually happening chemically is that this hydrogen here is going to want to switch places with Na. Now, why are they going to want to switch places? Well, to think about that, we need to think about the individual ions on the left side of that reaction. So remember, when we have these ionic compounds, we always have a positive ion bonded to a negative ion, right? It's that difference in attraction that's going to make them want to bond. So same idea here. We've got H plus and Cl minus bonded together. And what ends up happening is you're not going to want to bond two negatives. So what ends up happening is our positively charged ions, they're actually going to want to switch places. And that's what is happening in this chemical reaction. So our hydrogen is going to want to switch places with our sodium. And when that happens, you'll see that hydrogen is bonded to OH. It looks a little funky here because we know HOH, right? Hydrogen bonded to hydroxide. We know that as water, right? But you could also write it like I've written it above. Two H's, right? Bonded to one O. But I wanted to show it to you like that just so you can see where that H is coming from, that extra hydrogen. And then likewise, when sodium bonds with chlorine, right, we get NaCl out. But if you're wondering, hey, how did I know that the cations, the positive ions, were going to want to switch places? How come the hydrogen ion here doesn't want to bond with Na? Well, the reason for that is that both of those have positive charges, right? And remember, our positively charged ions are looking for negatively charged ions. They want to balance out. They want to be neutral. So that's not going to happen. So the only thing that's going to happen is your pluses can switch places, or your minuses can switch places, but that's essentially going to give you the same products, right? You're going to get NaCl and H2O. And this is generally how all these acid-base reactions, the neutralization reactions, are going to happen. So far, I've had you balance equations, but I haven't actually had you write out your own chemical reactions. So this says nitric acid, which is HNO3, can be neutralized by calcium hydroxide, or CaOH2. Write a balanced chemical equation for the reaction between these two compounds and identify the salt that it produces. So what are we given? Well, we know we have nitric acid, HNO3, reacting with calcium hydroxide. And actually, let's color code these. So I'll put acids in yellow and bases in blue. Okay, so we know we're reacting those two things. So we actually already know the entire left side of our equation. So let's go ahead and write that. We've got HNO3 in the aqueous form plus calcium hydroxide, also in the aqueous form, right? Those are both given to us up here. And we need to know, well, what comes out. We know we're reacting those two things. We know this is an acid-base neutralization reaction because I have an acid and I've also got a base. Generically, we're going to produce some water and some kind of salt, but we have to figure out what kind of salt. Okay, so in order to figure this out, before we can even start balancing, right, we have to know what's on the right side of the equation. So how do we figure that out? Well, we know that calcium is in group 2A, which means it's a metal, right? It's going to want to lose 2 electrons to be like the previous noble gas, which is argon in this case. So calcium has a 2+ charge. Hydroxide we're familiar with, right? Hydroxide ion is negative. Over here, we've got hydrogen bonded to, what's NO3? NO3 is nitrate, right? That's one of those polyatomic ions you had to memorize. So NO3 minus, and H plus is our hydrogen ion. So if you weren't sure which was your acid and which one was your base, how could you figure that out? Well, remember, Arrhenius said that anything that donates an H plus in solution is an acid, and anything that donates an OH minus in solution is a base. So we know which one's our acid and which one's our base, even if we're not told that. Okay, so what can we do here? Well, we know our positive ions are going to want to switch places. Whoops. They're going to want to switch places. If they stay bonded to who they're bonded with, right, then we don't actually really have a reaction occurring. So since we know there's a reaction occurring here, we're going to assume that they're going to switch places. So they will. So they're going to switch places. And now we have to figure out what we're making. So once they switch places, let's look at the first one first. So calcium is going to want to switch places with hydrogen, and it's going to be bonded to NO3. Now, before we do anything else, we need to make sure that this is bonded in the right ratio. Okay, so when they switch places, there might be 2 calciums bonded to 1 nitrate, or 2 nitrates bonded to 1 calcium, right? We have to know so that we are writing that formula correctly. So thinking back to chapter 3, right, we're making an ionic compound and we need to figure out what ratio they bond in. So if calcium has a 2+ charge and nitrate has a 1- charge, remember we can do our crisscross method, and we can take this 2 and pop it down there next to NO3. We can take this 1, pop it over here next to calcium, and that'll give us the ratio that they bond in. Or you could also think of it as, if calcium has a 2+ charge and we need this whole compound to be neutral, we need this whole compound to be neutral, then we've got to have 2 nitrates, right? Because we have 1- there, 1 times 2 is going to give us 2-, and that's going to cancel out with that 2+ here. Okay, so we've actually written our formula correctly. So what else do we make? Well, the next thing we have is hydrogen bonding with OH. So that's going to be H and OH, also known as what? Yeah, water, right? So we can just write that as water. Now, alternatively, since you know you make water and you know you make some kind of salt, you can just immediately write down water. right, as one of your products, and then just figure out what your salt is. But I like to show all the steps in the beginning. Okay, so our two positive ions from over here, they switched places, and we wrote out what they were making when that switch happens. That's the first step, is what are you making? That's the first question to ask yourself. What am I making from this reaction? What am I producing? What are my products? The next step is balancing, okay? So the next step is balancing. Oops. So now we have to make sure we know what reacts with what to give us what, but we need to know what ratio they all react in. So let's erase some of these notes here, and we'll go ahead and balance this. Pretty used to this, so we'll do it pretty quick. So listing out what I've got on the left, I've got H's, I've got N's, I've got O's, and I've got CA's. I've also got H's, N's, O's, and CA's on the right. Calciums, sorry. On the left, I've got a hydrogen here and 2 over here. So that's going to give me 3 hydrogens total on the left. Whoops, that's weird. And then for nitrogen, we've only got 1 on the left. Oxygen, we've got 2 from this area here and 3 from over here. So that's going to give us a total of 5 oxygens on the left. And then calcium, we've only got 1. All right, on the right, we've got, again, 1 calcium. Looks like we have 2 nitrogens, 7 oxygens, right? Because we have 6 from over here and 1 lonely one over there. And then we've got 2 hydrogens. Okay, so what I think I'm going to do is I'm going to make, I'm going to put a 2 here on our water and see what happens. And that's going to give me 4 H's. And I've got 6 oxygens over here plus now 2 over here. So that's going to give me 8 oxygens. Okay, so let's see. Now, well, I'm looking at that hydrogen and I'm thinking I've got 2 over here. So what if I had 2 here? That would give me 4, like I have on the right. So let's go ahead and do that. I'll put a 2 here, and that gives me 4 hydrogens. Now I've got to update, so I've got 2 nitrogens now, and looks like 6, 7, 8 oxygens. Okay, so that is the ratio of these reactants. It's a 2 to 1 to 1 to 2 ratio. We've balanced our chemical equation. Now, this question also asks for the salt that we produce. Oh, and I'm noticing I forgot to put the states here. So the water is going to be in the liquid state. And then the calcium nitrate is going to be in the aqueous state. Still dissolved in water. Okay, we started off dissolved in water and we're going to end dissolved in water. But I'm not too worried about those states for these reactions. I'm really more concerned with, can you write the product and can you balance the equation and identify the salt? Okay, well, if this is our water, right? This is the water that's produced from our, from our acid-base neutralization reaction. What's the other product I'm expecting to get out? Yeah, salt. So this must be our salt. And it is, right? It's an ionic compound that was produced by the reaction of an acid with a base. So here's my acid, here's my base, and I made my salt and water. Pretty cool, right? All right, so a lot of times with these acid-base reactions, like we saw up here, we want to know how much acid we need to react with how much of our base in order for them to be neutralized. Right? So in this practice problem, it says for one reaction, 16.8 grams of nitric acid is present initially. How many grams of calcium hydroxide are needed to neutralize that much nitric acid? All right, so before we do anything, looking at these 2 reactants that I have, and these are the same ones that we had above, which one's my acid and which one's my base? Try not to look at your notes. Yeah, so this one is going to be my acid, right? There's no OH minus that it can donate there, right? It's a hydrogen ion bonded to a nitrate ion. So that one's my acid. So this other one must be my base. And it is, right? It looks like I have calcium bonded to hydroxide. Okay, so before we've done anything, we've already identified our acid and our base. We've also got the balanced chemical equation up here. So I'm going to write that balanced chemical equation down here so that we have it right in front of us. And I'm going to leave off the states just for simplicity. Okay, so there's our balanced chemical equation. Okay, so in order to solve this problem, we've got to do a little bit of stoichiometry. But first I want to show you kind of the general setup. All right, so this is really similar. This setup for these problems is going to be very similar to the calculations we did in Chapter 6 for stoichiometry. And we've been practicing them since as well. So the idea here is we've got, we start with the mass of our first substance, and I'm going to just call that substance A. And we're trying to convert to the mass of our substance B. So we're trying to go from grams of A to grams of B. Anytime you're converting from some substance A to another completely different substance B, you have to have a balanced chemical equation. Why is that? Well, remember, the balanced chemical equation actually relates those two different substances. Otherwise, we have no ratio that relates those two things, right? So what we can do is if we want to get from grams of A to grams of B, just like those problems that we did for limiting reagents, you have to go through moles first. So I don't know any way of going from grams of A to grams of B in one step, but I do know an alternate route where I can go from grams of A to moles of A using what? Yeah, my molar mass of A. And then I can get from moles of A to moles of B using what? My balanced chemical equation, or my molar ratio. And then I can get from moles of B to grams of B using what? Yeah, the molar mass of B. This should look very familiar because we've been doing it since Chapter 6. It's just that now we're doing it specifically for an acid-base reaction, but it's the same setup. So let's try this out, knowing kind of our general strategy here. We need to go through moles. So I start with what I'm given. As always, I've got, some given amount of my first reactant, which is 16.8 grams of HNO3. And now I want to get from grams of HNO3 to moles of HNO3, right? Because I want to be able to relate moles of A to moles of B. So I have to get to moles first. Okay, so how do I get to moles from grams? Molar mass. So we got to find the molar mass of HNO3, and I'm going to let you do that off screen. I've already done it, so it's 63.01 grams of HNO3 is 1 mole of HNO3, right? Just taking our molar mass. All right, so that allows us to cancel out those grams of HNO3. And now in our next step, we want to get 2 moles of our other substance. Well, we're in moles of HNO3, and we want to get to moles of CaOH2. Okay, so where does moles of HNO3 need to go? Yeah, on the bottom. So 2 moles, right, from our balanced chemical equation, 2 moles of HNO3 go in, and 1 mole of calcium hydroxide goes in as well. That's the ratio, right? That's the ratio of those reactant. Okay, next step, now we're in moles of calcium hydroxide, right? We've canceled out moles of HNO3, nitric acid. Give myself a little more room here. And in the last step, we want to go from moles of calcium hydroxide to grams of calcium hydroxide, right? That's our goal, right? Grams of calcium hydroxide. Okay, so again, you're going to use the molar mass, this time of calcium hydroxide. And now we can cancel out those moles of calcium hydroxide, and we're left with grams of calcium hydroxide. All right, now you got to do that calculation, which means you take everything on the top and multiply it all together, and then divide by the product of everything on the bottom. And that's going to give us 9.88 grams of calcium hydroxide, which means what? We need 9.88 grams of calcium hydroxide in order to neutralize 16.8 grams of nitric acid. That's how many grams are required to neutralize that acid. All right, now in that question above, we were given grams and we wanted to get to grams. But a lot of times for these acid-base reactions, they're all occurring with aqueous solutions. Or they're dissolved in water. So sometimes instead of being given grams of your acid or base, you might be given the amount you have in mils, right? Some kind of volume, because we're now dealing with a liquid. The general problem-solving strategy is very similar. It's just now we're using molarity, which we practiced in the last chapter, using as a conversion factor. But let's show you how to do it again with these in this specific scenario. So this practice problem says, in a second reaction, 805 milliliters of 0.672 molar calcium hydroxide is present initially. What volume of 0.432 molar nitric acid solution is necessary to neutralize the calcium hydroxide solution? So again, we're using the same chemical reaction, so let's go ahead and copy it down here. And I get to use my handy-dandy tablet here, and I'm going to just copy this. There we go. Now we've got that right there. And let's just think about this strategy we've got here. So we start with milliliters and a known molarity. So just like we've been kind of using molarity as a conversion factor in other problems, we can use it as a conversion factor in these acid-base reactions as well. So here we start with liters of calcium hydroxide. We don't know how many liters. We were actually given that volume in milliliters, so we'll have to convert to liters first. But we do know how many milliliters, and we know how to convert from milliliters to liters, so that's a pretty quick step. So we're going to go from milliliters of calcium hydroxide to liters of calcium hydroxide. And then we want to get to moles of calcium hydroxide. Now again, why? Why do we want to get to moles? Yeah, remember, anytime we're going from some substance A to some substance B, the only thing that connects those two completely different substances is some kind of balanced chemical equation that relates the two of them, right? Or in other words, we need to get to moles so that we can use our molar ratio, right? Where 2 moles of this react with 1 mole of this. Okay, so just like before, we gotta get to moles in order to convert between these two very different substances. So our next step, after we get to liters of calcium hydroxide, we're gonna get to moles of calcium hydroxide. And to do that, we have to use molarity as our conversion factor. Right? We were given the molarity, which was 0.672 molar calcium hydroxide. And again, remember, anytime we have molarity, we can think of it as big M equals moles over liters. And so I'd urge you to rewrite that molarity as moles over liters. And that's just going to help you probably draw this conversion factor down here, where we've got 0.672 moles on the top and 1 liter on the bottom. Remember, moles per liter, miles per hour, 1 liter, right? Goes on the bottom, and the molarity stays with the moles. Okay, so we were given all of this information, so we're just using what we have in our tool belt. All right, so once we get to moles of calcium hydroxide, then we can use our balanced equation to get to moles of nitric acid. And then once we're in moles of nitric acid, we were also given the molarity of nitric acid. Right? Here is the molarity of nitric acid. So if we have moles of nitric acid, and we know we can use molarity as a conversion factor, which connects moles and liters, then we can use our molarity that we were given to convert to liters of nitric acid. Okay, so this is pretty complex. So let's try this out together. So we start with milliliters of calcium hydroxide. So let's do just like a separate step, converting from 805 milliliters into liters. As specifically, let's write down that it's calcium hydroxide. All right, well, 805 milliliters is 0.805 liters. So that equals 0.805 liters. Why did I want to convert to liters? Well, remember, we can only use liters and moles with molarity, so we got to get from milliliters to liters. Okay, so we've got that. So now in our second step, we can start our big long conversion factor. So we have 0.805 liters of our base, calcium hydroxide. Okay, and we want to know, well, how much of my acid do I need to add to my base to neutralize them? Okay, so we're in liters and we want to get to moles. We want to get to moles so that we can use our molar ratio, right? So in order to get from liters to moles, the only thing that connects liters and moles is molarity. So 0.672 moles go on the top. Moles of CaOH2 specifically. And in that many moles, there is 1 liter of CaOH2, right? That's how we break up that molarity. Remember, M equals moles per liter. So that's how I just broke this molarity into moles per liter. And now I'm left with moles of calcium hydroxide because our liters of calcium hydroxide are going to cancel, and I'm left with moles. I don't want moles of calcium hydroxide, I want moles of nitric acid. So we got to use our balanced chemical equation, this time with moles of calcium hydroxide on the bottom again. So it's going to be 1 mole of calcium hydroxide per every 2 moles of nitric acid. Cancel out those moles of calcium hydroxide. And now we're in moles of nitric acid. Okay, one more step here. And let me see if I can squeeze it in here and just kind of ignore this number here. So now we're in moles of nitric acid, and we wanted to get to liters of nitric acid, right? A unit of volume. Moles is not a unit of volume, liters is. So again, we can use our given molarity as a conversion factor, where we have 0.432 moles of HNO3 on the bottom and 1 liter of HNO3 on the top. Cancel out our moles of HNO3, and we're left with liters of nitric acid, which I did all of this off camera, and it's 2.50 liters of HNO3 solution are needed to neutralize.